Today we're going to talk about acid-base definitions, Arrhenius definitions, Bronsted-Lowry definitions, and Lewis definitions. We will start with Arrhenius definitions. Arrhenius acids form hydrogen ions. Remember, hydrogen ion is a positive ion. It is a hydrogen atom that has lost its electron, and so it is equivalent to a proton. Some examples of Arrhenius acids are hydrochloric acid, which again forms a hydrogen ion, hence it is an acid. Hydrocyanic acid also forms a hydrogen ion, so it is an acid. Note that the hydrochloric acid is a strong acid. It dissociates completely, producing many hydrogen ions, whereas hydrocyanic acid is a weak acid. Because it's in equilibrium, it produces few hydrogen ions. We say the equilibrium position is to the left since it is a weak acid. Arrhenius bases form hydroxyl ions. The hydroxyl ions are the OH minus ions. And examples of Arrhenius bases would be sodium hydroxide, a strong base, dissociating completely into sodium ions and hydroxyl ions. Calcium hydroxide is a weak base, dissociating only to a small extent, producing few hydroxyl ions. But again, the main thing is a base produces hydroxyl ions, acids produce hydrogen ions. Just because something contains hydrogen does not mean that it is an acid, for not all hydrogen atoms and compounds will ionize to form hydrogen ions. Ionizable hydrogen atoms must be in an ionic bond, that is, they must be bonded to a more electronegative element. If we look at the example of acetic acid, it has 4 hydrogens, but only one of those is ionizable. These are typically written in the first, indicating it's a positive ion, and then the second part is some kind of a negative ion, such as the acetate polyatomic ion. If we look at the molecular structure of acetic acid, here is the acetate polyatomic ion. Here is the ionizable hydrogen. These hydrogens are all attached to carbon. The electronegativity of hydrogen is 2.1. For carbon, it is 2.5. This makes an electronegativity difference of only 0.4, which means these bonds are covalent bonds, and therefore they will not break to dissociate hydrogen ions, and therefore that part of the molecule is not acidic. However, the hydrogen here is attached to an oxygen here. The electronegativity difference between the 3.5 value of the oxygen, the 2.1 is 1.4. Being much more electronegative, the electrons shift away from the hydrogen towards the oxygen, making this much more of an ionic bond, meaning this bond will break to release the positive hydrogen, so that makes this an ionizable hydrogen, or acetic acid an acid. You should be able to identify whether substances are Arrhenius acids or bases or neither. Typically, if the hydrogen is first, it is always an acid. So this is hydrocyanic acid, making that an acid. Again, hydrogen first, so this is an acid. Water you may think of as being neither an acid nor a base, but remember, water dissociates into hydrogen ions and hydroxyl ions. So since it produces hydrogen ions, it's an acid. It produces hydroxyl ions, it's a base, so it is both an acid and a base, something referred to as being amphoteric. If something can act as both an acid and a base, it is amphoteric. Sodium hydroxide is a base. And again, a reminder, not everything that has hydrogen is an acid. Here's a compound that has a hydrogen, but it is actually a base because it's covalently bonded to the oxygen in this case. This one is neither because it has neither hydrogens, so it cannot form a hydrogen ion. It doesn't have hydroxyls, so it cannot form hydroxyl ions. And this one is also neither an acid nor a base. The hydrogen is covalently bonded to itself, sharing that pair of electrons equally, so it will not dissociate to form hydrogen ions in any way, shape, or form. Going to Bronsted-Lowry definitions, Bronsted-Lowry acids are proton donors, and Bronsted-Lowry bases are proton acceptors. So a proton is the same as a hydrogen ion. Remember that an Arrhenius acid forms hydrogen ions. Bronsted-Lowry acids form protons, which are the same as a hydrogen ion. So those definitions are pretty much the same. Bronsted-Lowry bases, on the other hand, are proton acceptors. That is not the same thing as forming hydroxide ions. However, anything that forms a hydroxide ion can also accept a hydrogen ion, so all Arrhenius bases are Bronsted-Lowry bases, but not all Bronsted-Lowry bases are Arrhenius bases. Moving on to another definition, a conjugate base is what is formed when an acid gives up a hydrogen ion, and a conjugate acid is what is formed when a base accepts a hydrogen ion. Let's look at this example here. We wanted to find both acid and base, and conjugate acid and conjugate base. Note this is a reversible reaction. It goes both ways. In the forward direction, the H3PO4 is going to change into H2PO4. The H2O is going to change to H3O, meaning this is losing a hydrogen ion, and the water is gaining a hydrogen ion. So since the H3PO4 is losing the hydrogen ion or donating the hydrogen ion, that is the acid. The water is accepting it, that is the base. And then if we look at our definitions of a conjugate base, the conjugate base is what is formed when an acid gives up a hydrogen ion. So the H3PO4 is giving up the hydrogen ion, therefore it is the conjugate base, the species that is donated or formed when an acid gives up the hydrogen ion. And the hydronium ion is the conjugate acid. It is what is formed when a base accepts a hydrogen ion. We can also look at the reverse direction. If the hydronium ion is going to change back into water, it has to give up its hydrogen ion to the H2PO4, and when the H2PO4 receives that hydrogen ion, it goes back to the H3PO4. So since this is giving the hydrogen ion, it's the conjugate acid in the reverse direction. Since this is accepting it, it is the base or conjugate base in the reverse direction. Do a couple more here, make sure you understand this. Note here we have HNO2 on the reactant side. Product side, we have only NO2, and so it's losing a hydrogen ion, and so it must therefore be the acid giving the hydrogen ion. The H2O therefore must be the base accepting the hydrogen ion, and when we see H3O, that indicates that the water has gained a hydrogen ion. Likewise, when the base accepts the hydrogen ion, it becomes the conjugate acid. When the acid gives up the hydrogen ion, it becomes the conjugate base. In our second example here, PO4 cannot be an acid since it does not have a hydrogen to give. And if we look on the product side, we can see it has received a hydrogen ion. And so the water must be acting as the acid, giving the hydrogen ion to the PO4 3-. Therefore, it is acting as the base. And again, when the acid gives up the hydrogen ion, it becomes the conjugate base. When the base accepts the hydrogen ion, it becomes the conjugate acid. If we compare these two examples, water is acting as an acid in the second example, but it's acting as a base in the first example. Again, that demonstrates that water is amphoteric. It is acting as an acid in some cases, bases in another case. Again, you should be able to identify things as Bronsted-Lowry acids or bases. And this is an acid since it has the hydrogen first. This one is neither. Methane is covalently bonded. Again, there's very similar electronegativities between the carbon and the hydrogen. Therefore, that is a fully molecular compound and will not ionize. Water is both an acid and a base. Again, it is amphoteric. Sodium hydroxide can accept a hydrogen ion to form water. Therefore, it is a Bronsted-Lowry base. Aluminum chloride is neither an Bronsted-Lowry acid nor Bronsted-Lowry base. Our last two examples are Bronsted-Lowry bases because both of these can accept a hydrogen ion. The ammonia can accept a hydrogen ion to form the ammonium polyatomic ion. Nitrogen has an unshared pair of electrons that will hydrogen bond to the hydrogen, and the negative charge here will attract a hydrogen, and that will form HNO2. So here are two examples of Bronsted-Lowry bases that are not Arrhenius bases because they cannot form hydroxyl ions. Again, all Bronsted-Lowry, all Arrhenius bases are Bronsted-Lowry bases because they can always accept a hydrogen ion, but not all Bronsted-Lowry bases are Arrhenius bases because they don't form the hydroxyl ion. Monoprotic acids are defined as those acids that have only one hydrogen ion atom that will ionize. Diprotic acids have two protons or hydrogen atoms that will ionize, and triprotic have three, so mono 1, di 2, tri 3, and so HCN is a monoprotic acid having only one hydrogen. Acetic acid, even though it has four hydrogens, has only one that will ionize, this first one, so it is considered a monoprotic acid. H2SO4 is a diprotic acid having two hydrogens, and phosphoric acid is a triprotic acid having three hydrogens. Last definition, Lewis definitions. Lewis bases are electron pair donors, and Lewis acids are electron pair acceptors. If we look at the example given here, the ammonia molecule is going to bond to the boron trifluoride molecule. Here is the bond that is formed. To determine which one is the Lewis acid, Lewis base, we have to ask ourselves, where did that pair of electrons come from? It comes from the ammonia, so that is our Lewis base. The boron trifluoride is going to accept that pair of electrons when the bond is formed. Therefore, it is our Lewis acid. One more example. If we look at a proton, a hydrogen atom, it can never be a Lewis base because it does not have an electron pair to donate. If we look at the water molecule, it has two unshared pairs of electrons that it could donate. And on the product side, we see the hydrogen bonded to the water molecule. That line there represents a shared pair of electrons that must have come from the water. So the water is the Lewis base and the proton is the Lewis acid.